You imagine nothing as darkness, empty space, a void waiting to be filled. But physics doesn't allow that. In quantum field theory, what we call empty space seethes with energy. Particles flash into existence and vanish. The vacuum itself has measurable weight. So when you picture nothing before the Big Bang, you're probably picturing something that cannot exist. And here's where it gets stranger. The word before assumes time was already there, ticking away, waiting for the universe to show up. But time is not a stage. Time is not a container. According to general relativity, time is woven into the fabric of the universe itself, which means if the universe began, time began with it. So asking what came before the Big Bang might be like asking what's north of the North Pole. The question contains a direction that doesn't exist. You've been asking this question your entire life, but the question itself may be broken. If ideas like this refuse to let your mind rest, stay with us as we follow the quiet clues physics leaves behind. Let's start with something simpler than the universe. Let's start with a room. You walk into a room and turn off the lights. You close the door. You remove every object, every molecule of air, every atom. You cool it to absolute zero so even thermal radiation stops. You've created the empty space you can imagine. Is it nothing? No. Even in that room, quantum fields still exist. The electromagnetic field is there. The electron field. The quark fields. These aren't made of matter. They're more fundamental than matter. They're the scaffolding reality is built on, and they never turn off. In the 1940s, Dutch physicist Hendrik Casimir predicted something strange. If you place two uncharged metal plates very close together in a vacuum, they should attract each other, not because of gravity or electromagnetism, but because the quantum fields between the plates are slightly suppressed compared to the fields outside. This was tested. The plates move toward each other. The vacuum has force. It has structure. It pushes and pulls on things. This is what physicists mean when they say the vacuum has energy. It's not poetic language. It's measurable. The empty space we can create is still humming with quantum activity we cannot remove. So nothing, in the physical sense, doesn't exist. But you might say, fine, quantum fields exist in our universe. But before the Big Bang, couldn't there have been true nothing? No fields, no space, no quantum anything. This is where intuition starts to fail. Because what you're proposing is a state of absolute nothing giving rise to everything. And physics has never observed anything appearing from true non-existence. Every quantum fluctuation, every particle pair that pops into being, does so within an existing framework of fields and space-time. Nothingness doesn't seem to be an option the universe allows. But let's push further. Let's ask why. Think about symmetry. If you have a perfectly round ball, it looks the same no matter how you rotate it. Physicists call this rotational symmetry, and there's a deep principle in physics. Symmetries correspond to conservation laws. Rotational symmetry gives you conservation of angular momentum. Time symmetry gives you conservation of energy. Emmy Noether proved this connection in 1915, and it's one of the most profound insights in all of physics. Now here's the uncomfortable part. Absolute nothingness would be perfectly symmetric. No properties, no structure, no variation anywhere. It would be the same in every direction, at every point, in every way. But perfect symmetry is unstable. Consider a pencil balanced on its tip, perfectly symmetric, but the slightest perturbation and it falls. Symmetry breaks. This isn't a flaw in the pencil. It's a feature of symmetric states. They're often unstable equilibria. In quantum mechanics, this instability is worse. Quantum systems don't just sit still, they fluctuate. And if there's any possible lower energy state, any configuration with less energy, quantum tunneling allows the system to jump there. So if true nothingness were possible, and if it's symmetric, and if there's any lower energy state available, including existence itself, then nothing wouldn't stay nothing. It would decay into something. This isn't speculation. We see symmetry breaking everywhere in physics. The early universe, according to our models, went through several phase transitions where symmetric states broke into less symmetric ones. The Higgs field settled into a non-zero value, giving particles mass. The strong and electroweak forces separated. Symmetry breaks. That's what the universe does. And the ultimate symmetry, total non-existence, may be the most unstable state of all. Now notice what this quietly implies. It implies that existence might not need a cause. Not in the way we usually think about causes. If nothingness is unstable, if it naturally decays into something, then the universe doesn't require an external push. It would emerge the same way a pencil falls, not because something knocked it over, but because the alternative was unstable. But we're getting ahead of ourselves. Let's pull back and ask a more basic question. What is time? You experience time as a river. It flows forward. Past is behind you, future ahead, present is this moment now. This seems obvious, fundamental, beyond question. Physics sees it differently. In Newton's mechanics, time is absolute, a universal clock ticking the same for everyone everywhere. But Einstein showed this is wrong. In special relativity, time is relative. Two observers moving at different speeds will disagree about which events are simultaneous. They'll disagree about how much time passed between events. Time is not absolute. It's not separate from space. They're woven together into space-time, a four-dimensional fabric where time is just one direction among four. And here's what matters for our question. In general relativity, space-time can be curved, stretched, compressed. Near a massive object, time runs slower. Near a black hole's event horizon, time slows to a crawl relative to distant observers. Inside the event horizon, the geometry is so warped that all paths lead toward the singularity. The future becomes spatial. Time is part of the geometry of the universe. So if the universe has a beginning, time has a beginning. There's no time before the Big Bang for the same reason there's no north before you reach the North Pole. The dimension simply doesn't extend that direction. But this creates a puzzle. We're used to thinking causally. Event A causes event B, which causes event C causes come before effects. But if time itself begins with the Big Bang, then there's no before for a cause to exist in. So what caused the Big Bang? The question assumes time already existed. It sneaks in the very thing we're trying to explain. This is where language starts to break down. We're asking about a regime where our normal concepts, forged by evolution to navigate a world of medium-sized objects moving at slow speeds, simply don't apply. But physics doesn't stop at the boundary of language. It keeps going. It builds models. It makes predictions. It tests them. And what physics has discovered is stranger than wordlessness. In the 1980s, physicist Alan Guth proposed cosmic inflation. The idea was simple. In the first fraction of a second after the Big Bang, the universe expanded exponentially. Not just fast, exponentially. Space itself stretched so rapidly that regions which had been close enough to interact were suddenly separated by vast distances. This solved several problems. It explained why the universe looks so uniform in all directions even though distant regions couldn't have communicated. It explained why space is so flat. It explained the pattern of small density variations that eventually became galaxies. But inflation did something else, something quieter. It pushed the actual beginning, the true moment of origin, outside the observable universe. Let me explain. If inflation happened, the region we can see today, the entire observable universe with its hundreds of billions of galaxies, all of it came from a tiny patch much smaller than an atom. And inflation stretched that patch so violently that anything outside it is now receding from us faster than light. We're not seeing the actual beginning anymore. We're seeing the aftermath of inflation. The moment when exponential expansion ended and normal expansion took over. The true beginning, if there was one, is beyond what we can observe. But inflation raises a question. What started it? In Guth's original model, inflation is driven by a field called the inflaton. This field has potential energy, and like a ball rolling down a hill, it slowly decreases. While it's high, it drives exponential expansion. When it reaches the bottom, inflation ends and the field's energy converts into particles and radiation. The hot Big Bang begins. But where did the inflaton come from? And where did the energy come from to drive inflation? Here's where quantum mechanics enters. In quantum field theory, fields have a lowest energy state. But that state is not zero. It's called the vacuum energy or 0-point energy. Even at absolute zero temperature, even with no particles present, fields still have this residual energy, and in some configurations, this vacuum energy can be enormous. If the inflaton field started in a high energy state, what we call a false vacuum, then its vacuum energy could drive inflation. The field doesn't need to borrow energy from anywhere. The energy is already there, inherent in the field's configuration. But this pushes the question back. Why was the field in a high energy state? One answer is quantum tunneling. Imagine a ball sitting in a valley. It's stable there, but beyond the hill is a deeper valley. Classically, the ball can't get there. It doesn't have enough energy to roll over the hill. quantum mechanically it can tunnel through. This isn't metaphor. Particles do this. An electron in an atom can tunnel through a barrier it shouldn't classically be able to cross. Alpha particles tunnel out of atomic nuclei in radioactive decay. Tunneling is how scanning tunneling microscopes work. The probability depends on the barrier's height and width. For big objects, the probability is absurdly small. But for quantum fields in the early universe, it becomes relevant. So here's a model, proposed by physicists like Alexander Vilenkin and Andrei Linde. Imagine a state of no space, no time, no fields. True quantum nothingness, if such a thing is possible. This state has some quantum amplitude, some probability of existing, but it's unstable. Through quantum tunneling, it can decay into a state with a tiny bubble of space-time. Inside this bubble, the inflaton field is in a high-energy state. That high energy drives inflation, and the bubble expands exponentially. Time begins with the bubble. Space begins with the bubble. There is no before, because time is part of what's being created. This is called quantum tunneling from nothing. It sounds absurd, and maybe it is, but it's a serious model in cosmology, and it makes predictions. Some versions predict particular patterns in the cosmic microwave background, the afterglow of the Big Bang. Those predictions can be tested. But notice what's happened here. We haven't answered what came before the Big Bang. We've dissolved the question. We've shown that before assumes time already existed, and if time itself is part of what emerges, then the question is malformed. It's not that we don't know the answer, it's that the question has no meaning. This is deeply uncomfortable. Our minds want a cause. We want to know what started it all, but quantum mechanics doesn't always give causes. It gives probabilities. An atom decays, and we can calculate the probability. But there's no cause for this particular atom decaying at this particular moment. It just happens. And if the universe emerged through a quantum process, the same might be true cosmologically. The universe began not because something caused it, but because it was quantum mechanically possible. But let's be careful. This is a model, one model among several, and it makes assumptions. It assumes quantum mechanics applies even in the absence of space-time. That's a big assumption. Quantum mechanics, as we know it, is formulated on a background of space and time. Can it work without that background? We don't know. It assumes the concept of nothing even makes sense. We've already seen that physical nothingness in our universe doesn't exist. Can it exist outside our universe? The question may be incoherent, and it assumes the laws of physics themselves exist prior to the universe. But laws of physics describe regularities in how things behave. If there are no things, are there laws? This is where physics reaches its boundary, not because physicists stop caring, but because the tools we have, mathematics, observation, experiment, all depend on there being something to study. We're trying to use the map to understand what came before the territory. Okay, let's think about laws of physics differently. You might imagine laws as rules the universe follows, like legislation. The universe checks the rule book and obeys. But that's not how it works. Laws of physics are descriptions, patterns we've noticed. When we say F equals ma, we're not saying the universe computes this equation. We're saying we've observed a regularity force is proportional to mass times acceleration. The equation is our description of the pattern. And here's what's interesting. Many physicists suspect the laws of physics are not arbitrary. They're constrained by deeper principles: symmetry, consistency, mathematical structure. For instance, the laws of electromagnetism can be derived from demanding that the theory be symmetric under certain transformations. The laws of general relativity can be derived from the principle that physics should look the same to all observers. These aren't random rules someone made up. They're the consequences of demanding consistency. And some physicists go further. They suggest that mathematics itself constrains what's possible, that the universe is, in some sense, mathematical. Not that it follows mathematical laws, but that it is a mathematical structure. This is controversial. It sounds mystical, but there's a thread of reasoning behind it. If the universe has no arbitrary features, no free parameters that could have been otherwise, then it might be uniquely determined by pure logic and mathematics. And if that's true, then asking why the universe exists becomes like asking why the number 3 is prime. It's not caused. It's just a consequence of what numbers are, but this shifts the mystery. Now we're asking why mathematics exists, or why logic exists, or why anything is rather than nothing, and we're back where we started. Except now we see the question more clearly. The question isn't about a moment in time before the Big Bang. It's about the framework itself. Why is there a framework? Why are there laws, quantum fields, space-time, mathematics? Why is there something rather than nothing? This question has haunted philosophy for millennia, and physics, despite its astonishing progress, hasn't answered it. Physics takes the existence of something as given and explores its behavior. But here's what physics has done. It's shown that nothing is harder to define than you think. It's shown that existence might not need a cause in the traditional sense. It's shown that time itself might be part of what needs explaining, not part of the framework we use to explain other things. And it's shown that the universe is far stranger than our intuitions suggest. So let's talk about the cosmological constant. In 1917, Einstein added a term to his equations of general relativity. He called it the cosmological constant. It represented a kind of energy inherent in space itself. Not energy in space, but energy of space. Einstein introduced it to make his model of the universe static. At the time, astronomers thought the universe was unchanging, but general relativity predicted it should either expand or contract. So Einstein added the cosmological constant to balance gravity and keep the universe still. Then Edwin Hubble discovered the universe is expanding. Einstein reportedly called the cosmological constant his biggest blunder. He removed it from his equations, but the universe didn't care what Einstein thought. In the 1990s, astronomers measuring distant supernovae discovered that the universe's expansion is accelerating. Something is pushing space apart. They called it dark energy. And the simplest explanation for dark energy is the cosmological constant, energy inherent in empty space. This is vacuum energy. The same thing we talked about earlier with quantum fields. Space has energy just by existing. Now here's the puzzle. When you calculate how much vacuum energy quantum field theory predicts, you get an absurdly large number, so large that the universe should be ripping apart. But when you measure the actual dark energy density, it's tiny, about 1/20 orders of magnitude smaller than the prediction. This is called the cosmological constant problem, and it's one of the deepest unsolved problems in physics. But for our question, it tells us something important. Space is not nothing, even empty space, even space with no particles, no fields in excited states, no anything. The vacuum itself has energy, and this energy is positive. It's not zero, it's not negative, it's positive, which means the vacuum is not the lowest energy state. Could there be something lower? Some physicists think so. They suggest our vacuum is metastable. It looks stable, like the ball in the valley, but there might be a deeper valley somewhere. And if that's true, the vacuum could decay. This is called vacuum decay or false vacuum decay. If it happens, a bubble of lower energy vacuum would form somewhere in the universe and expand at the speed of light, destroying everything in its path. The physics inside the bubble would be different. Particles would have different masses. Atoms wouldn't form. The bubble would be lethal to life. But don't worry, if our vacuum is metastable, the decay rate is probably so low that it won't happen for trillions upon trillions of years, if ever. The point is this: the vacuum is not the end of the story. It has structure, it has energy, it can change. And in the earliest moments of the universe, according to inflation, the vacuum did change. It started in a high energy state and decayed into a lower one. That decay released energy, which became the matter and radiation we see today. The universe didn't come from nothing. It came from a transition between vacuum states. But where did those vacuum states come from? Here's where we hit the recursion. Every answer generates a deeper question. Every explanation assumes something. We can explain the Big Bang with inflation, but inflation assumes quantum fields and space-time. We can explain inflation with quantum tunneling, but that assumes quantum mechanics. We can explain quantum mechanics with mathematics, but that assumes logic. At some point, we reach bedrock. Things we cannot explain because they're the foundation we use to explain other things. Or maybe there is no bedrock. Maybe it's turtles all the way down. Or maybe the whole framework of explanation, of cause and effect, of things coming from other things, breaks down at the ultimate boundary. Let's consider time again, but differently. You experience time as flowing. The present moment moves forward. The past recedes, the future approaches. But in physics, especially in relativity, time doesn't flow. It just is. This is called the block universe or eternalism. All of space-time exists at once. Past, present, future, all equally real. The flow of time, the sense that the present is special, is something our consciousness adds. It's not in the physics. If this is true, then the Big Bang doesn't happen. It exists. It's a location in space-time, about 13.8 billion years in the past direction from here, but it's not an event that occurred and is now over. It's a permanent feature of the space-time manifold. There's no creation in the sense of something starting to exist. There's just existence, four-dimensional, eternal in a timeless sense. This dissolves the question differently. Instead of asking what caused the Big Bang, we ask why the space-time manifold has the shape it does. Why is there a boundary in the past direction? Why does time have a beginning? And maybe it doesn't. Some models, like the Hartle-Hawking no-boundary proposal, suggest that time near the Big Bang becomes space-like. The distinction between space and time blurs. The universe doesn't have a boundary in time. It's finite but boundless, like the surface of a sphere. You can travel around a sphere forever without hitting an edge, and similarly, you might travel back in time toward the Big Bang without ever reaching a beginning. This is hard to visualize. Our brains aren't built for it, but mathematically, it's coherent. In this model, asking what came before the Big Bang is like asking what's south of the South Pole. The question assumes a direction that doesn't exist, but the Hartle-Hawking proposal makes a big assumption. It uses Euclidean time, a mathematical trick where time is treated as another spatial dimension. This makes the equations easier to solve, but it's not clear what it means physically. Is time really becoming space like near the Big Bang, or is this just a mathematical tool? We don't know, we can't observe it. The Planck error, the first tenth for 3 seconds, is beyond what our theories can handle. Quantum mechanics and general relativity give contradictory answers in that regime. We need quantum gravity, and we don't have it yet. So we're working with models, educated guesses, frameworks that might be right but haven't been tested. And this is worth sitting with. Physics has made astonishing progress. We understand the universe back to fractions of a second after the Big Bang. We can describe the formation of atoms, stars, galaxies. We can predict the cosmic microwave background and measure it to exquisite precision. But the ultimate beginning, the moment of origin, is still beyond us. Not because we're not smart enough, not because we haven't tried hard enough, but because we're asking about a regime where our tools, quantum mechanics, general relativity, break down. We're at the edge of what physics can currently say, and that's okay. Science doesn't pretend to have all the answers. It explores, it builds models, it tests them, and when it reaches the limit of what it knows, it admits that openly. This honesty is part of what makes science powerful. 2. Let's think about what beginning means. In everyday life, beginnings are clear. You start a journey, you begin a book, you're born. But these beginnings assume time already exists. The journey begins at a particular moment. Birth happens at a particular time. But if time itself begins, what does that mean? One way to think about it, the universe doesn't begin in time. Time begins in the universe. This is a subtle shift. You're not imagining a clock ticking and then suddenly the universe appears. You're imagining time itself as part of what's being created. General relativity allows this. Space-time is a dynamical object. It can curve, expand, contract, and it can have boundaries. A boundary in time is a beginning, but boundaries are tricky. In mathematics, a boundary is not part of the space. The edge of a disk is not on the disk. It's where the disk ends. Similarly, if space-time has a boundary in the past, the Big Bang itself might not be part of space-time. It's where space-time ends, or begins, depending on your direction. This means there's no moment of the Big Bang, no instant when it happened. The Big Bang is the limit you approach as you go back in time, but you never reach it. It's like the number 0 on the number line. You can get arbitrarily close, but 0 itself is the boundary, not a number you reach from the positive side. But this creates a strange situation. If there's no first moment, then there's no moment before the first moment. The question, what came before, doesn't just have no answer. It has no meaning. This is hard to accept. Our minds want a first cause, a starting point, a reason. But the universe doesn't owe us intuitive answers. And here's something else to consider. Some models suggest time might be cyclic. The universe expands, contracts, bounces, expands again. In these models, the Big Bang isn't the beginning. It's a transition from a previous phase. This avoids the problem of a first cause by denying there is a first. It cycles all the way back, but cyclic models have problems too. Entropy, for instance. The second law of thermodynamics says entropy always increases. In a cyclic universe, entropy would build up cycle after cycle. Eventually, the universe would reach maximum entropy, a heat death, and cycles would stop. Unless there's a mechanism to reset entropy, but we don't know of one, or unless the cycles aren't quite identical. Maybe each cycle is different, and entropy has meaning only within a cycle, not across cycles. This is speculative, but it's being explored. The point is, physicists are trying different frameworks, beginning with a Big Bang. No beginning, just eternal cycles. No boundary in time. Each framework has strengths and problems. We don't know which, if any, is right, but we're narrowing the possibilities. We're testing predictions. We're learning what the universe is not, even if we haven't figured out what it is. Let's talk about observation. Quantum mechanics tells us that measurement affects reality. Before you measure a particle's position, it's in a superposition of many positions. Measurement collapses the superposition. The particle becomes localized. This is strange, but it's been tested endlessly. It's how the world works at quantum scales. Now apply this to cosmology. If the early universe was a quantum system, and it was in a superposition of many states, when did it collapse into the state we observe? One answer: it hasn't. In the many worlds interpretation of quantum mechanics, superpositions don't collapse. They branch. Every quantum possibility happens in different branches of reality. If this is true cosmologically, then the Big Bang didn't produce one universe. It produced all possible universes. We're in one branch. Other versions of us are in other branches, and there are branches with no us at all. This is mind-bending, but it takes quantum mechanics seriously. It doesn't add a collapse mechanism. It just follows the equations. In this framework, asking why the universe has the properties it does is like asking why you were born in this country and not another. You were born in all countries. You're just experiencing this branch. The universe doesn't have properties. Branches have properties. And we find ourselves in a branch compatible with our existence. This is called the anthropic principle. The universe seems fine, tuned for life, not because it was designed, but because we couldn't observe a universe incompatible with life. We're here because this branch allows us to be here. But this raises questions too. If all branches exist, what determines the measure? Why are some branches more common than others? And does exist even mean something if you're talking about branches you can never observe? These are open questions. Physicists argue about them. There's no consensus. But the many worlds interpretation does something interesting. It removes the specialness of the Big Bang. The Big Bang isn't the creation event. It's a branching event, and branching events happen constantly at every quantum interaction. Creation is happening all the time in a sense. New branches splitting off, new universes being born. The Big Bang is just the earliest branch we can trace back to. But even this assumes time goes back to the Big Bang, and we've already questioned that. Here's another angle. Information. In classical physics, information can be destroyed. You burn a book, the information is gone. But in quantum mechanics, information is conserved. This is called unitarity. The total information in a closed system never decreases. Black holes seem to violate this. Stuff falls into a black hole, and the information seems lost. Hawking radiation coming out of the black hole is thermal, random, containing no information about what fell in. But this led to the black hole information paradox. If information is lost, quantum mechanics is wrong. If information escapes, we don't know how. Physicists have been wrestling with this for decades, and the current thinking is that information is not lost. It's encoded somehow, perhaps in the subtle correlations of Hawking radiation, perhaps in the structure of space-time itself. But if information is conserved, what about the Big Bang? If the universe came from nothing, where did all the information come from? One answer: the total information is zero. This sounds paradoxical, but it's possible. If every bit of information is paired with its opposite, the total sums to zero. The universe contains vast amounts of information, but it's balanced, positive and negative, particle and antiparticle, matter and antimatter, except we observe more matter than antimatter. The asymmetry is small, but it's there. So the total information isn't exactly zero. There's a remainder, a net bit. Where did that come from? Maybe it was always there. Maybe even nothing. Has structure, has a minimal amount of information, and the universe is the unfolding of that. Or maybe information isn't fundamental. Maybe it's emergent, a higher level description of something deeper. This is where physics blurs into philosophy. We're not just asking about the beginning of the universe. We're asking about the nature of reality. Is information fundamental or emergent? Is space-time fundamental or emergent? Are particles fundamental or emergent? Some physicists think everything is emergent, that there's a deeper level, maybe a network of abstract relations, maybe pure mathematics, and what we call particles and forces and space-time are just patterns in that deeper substrate. Others think we'll never reach a fundamental level, that it's turtles all the way down, each level explained by a deeper one, forever. And others think we're asking the wrong questions, that the framework of reductionism, of explaining things by breaking them into parts, fails at some point, that the universe is holistic, irreducible, a unified whole that can't be decomposed. We don't know, but we keep pushing. We build accelerators to probe smaller scales. We build telescopes to observe earlier times. We develop new mathematics to describe regimes our old tools can't handle. And slowly we learn. Let's return to vacuum energy, but from a different direction. The vacuum energy density as measured by dark energy is incredibly small but not zero, about 10⁹ joules per cubic meter. This is strange because quantum field theory predicts it should be enormous. About 10⁻13 joules per cubic meter. That's 120 orders of magnitude too big. Why is it so small? Nobody knows. This is the cosmological constant problem, and it's been called the worst prediction in the history of physics. But here's another puzzle. The vacuum energy density is small, but it's not zero. Why not exactly zero? In particle physics, symmetries often enforce quantities to be zero. If a theory has a certain symmetry, that symmetry forbids certain terms. They have to be exactly zero. But the cosmological constant doesn't seem to be protected by any symmetry. It can be any value, and yet it's not zero. It's tiny but not zero. Some physicists think this is a clue. If the cosmological constant could be any value, and different regions of the universe, or different universes in a multiverse, have different values, then we would find ourselves in a region where the value is small. Why? Because if it's too large, galaxies don't form, stars don't form, planets don't form, life doesn't arise. We couldn't exist in a region with a large cosmological constant. This is anthropic reasoning. The cosmological constant is small because if it weren't, we wouldn't be here to ask why. But this feels unsatisfying. It's not an explanation. It's an observation about selection bias. Still, if the multiverse is real, and different regions have different physical constants, anthropic reasoning might be the only explanation available. We're here because this region is habitable. Other regions aren't. There's no deeper reason. But this assumes the multiverse, and we have no direct evidence for it. The multiverse is predicted by some versions of inflation, eternal inflation, where inflation never completely stops but ends in some regions while continuing in others. Each region where inflation ends becomes a universe. Different regions might have different properties, but we can't observe other universes. By definition, they're outside our light cone. We can't test the multiverse hypothesis directly. We can only test its predictions for our universe, and those predictions are often vague. They say certain properties could vary, not what they will be. So the multiverse remains speculative, useful for thinking but not confirmed. And even if it's real, it pushes the question back. Where did the multiverse come from? What started eternal inflation? We're back to the same problem. So let's think about causation more carefully. In everyday life, causes precede effects. You flip a switch, the light turns on. The flipping causes the lighting. But in physics, causation is subtler. In special relativity, events can only influence each other if they're connected by a light speed path. If two events are space-like separated, meaning you'd have to travel faster than light to get from one to the other, then neither can cause the other. So causation is tied to the structure of space-time, to light cones, to the geometry of possible influences. In quantum mechanics, causation gets even stranger. You can have entanglement where measuring one particle instantly affects another, no matter how far apart. But this doesn't allow faster than light signaling, so it's not causation in the usual sense. It's correlation without a causal mechanism. And in quantum field theory, particles can be created and destroyed. A photon can split into an electron and positron, which then annihilate back into a photon. Did the photon cause the particles, or did the particles cause the photon? The question doesn't quite make sense. What exists is a field, and particles are excitations of that field. Causation is a higher, level concept we use to describe patterns in the field's behavior. Now apply this to the universe. If the universe is fundamentally quantum, then causation might not be fundamental either. It might be emergent, a pattern we observe at large scales, but that breaks down at the quantum level. And if causation is emergent, then asking for the cause of the universe might be incoherent, like asking for the color of justice. The question uses a concept that doesn't apply. The universe doesn't have a cause, not because it's uncaused, but because causation is something that happens within the universe, not to the universe. This is a profound shift in thinking. We're so used to causes that we assume everything has one. But maybe causation is like temperature. Temperature is a property of large collections of particles. It doesn't make sense to ask the temperature of a single atom. Similarly, causation might be a property of macroscopic systems embedded in time. It doesn't make sense to ask the cause of time itself. But this doesn't satisfy the itch. We still want to know, why is there a universe at all? And physics, at this point, can't answer, not because physicists are stumped, but because the question might be outside the scope of physics. Physics describes how things behave. It doesn't explain why there are things in the first place. That's a metaphysical question. And metaphysics, while fascinating, isn't science. Let's talk about the Planck scale. In quantum mechanics, there's a fundamental unit of action called Planck's constant. It sets the scale of quantum effects. In general relativity, there's a fundamental coupling constant, the gravitational constant. It sets the strength of gravity. When you combine these with the speed of light, you can form natural units. The Planck length, about 10^35 meters. The Planck time, about 10^43 seconds. The Planck energy, about 1 billion joules. These aren't arbitrary. They're the scales where quantum mechanics and gravity become equally important. Below the Planck scale, space-time itself becomes quantum. It's not a smooth fabric anymore. It's a roiling foam of quantum fluctuations. Space and time lose their usual meaning. We don't have a theory of quantum gravity yet. String theory is a candidate. Loop quantum gravity is another, but neither is confirmed. So we can't describe what happens at the Planck scale. We can't model the first 10^43 seconds of the universe. This is called the Planck error. It's a wall beyond which our physics doesn't reach. Everything before the Planck error is speculation, educated guesses based on incomplete theories. And the Big Bang, the moment of origin, is within the Planck error. So we can't describe it. Not yet. This is frustrating. We're so close. We can describe the universe back to an unimaginably early time, but the beginning itself remains out of reach. But here's what's interesting. Some physicists think the Planck scale is the smallest meaningful scale, that space-time is fundamentally discrete, not continuous, that there's a minimum length and a minimum time, and you can't subdivide further. If that's true, then the notion of an instant, a dimensionless point in time, doesn't exist. Time is made of Planck scale moments, and the Big Bang isn't a point, it's a region. This would change the question. Instead of asking what happened at the Big Bang, we'd ask what happened during the Planck era, and the answer might be space-time was quantum, fluctuating, and our classical notions of before and after don't apply. There's no moment of creation. There's a fuzzy quantum region where space-time emerges. This is still speculative, but it's a direction of thought, and it dissolves the question again, in a different way. Let's consider the role of mathematics. Physics is written in mathematics. The laws are equations. The predictions are calculations. But why does mathematics work so well? Eugene Wigner called this the unreasonable effectiveness of mathematics. Why should the abstract patterns mathematicians study, often for purely aesthetic reasons, turn out to describe the physical world? One answer: mathematics is the language of structure, and the universe has structure. Any structured system can be described mathematically. But there's a stronger claim some physicists make, that the universe isn't just described by mathematics, it is mathematics. This is the mathematical universe hypothesis proposed by Max Tegmark. If the universe is a mathematical structure, then asking why it exists is like asking why prime numbers exist. They don't need a cause. They're necessary truths of logic. But which mathematical structure? There are infinitely many. Why this one? Tegmark's answer: all of them exist. Every consistent mathematical structure is a universe. We're in one such structure. Other structures are other universes unreachable from ours. This is the ultimate multiverse. Not just different regions of space-time, but different mathematical structures, different laws of physics, different kinds of particles. different geometries. If this is true, then the question, why this universe, has the same answer as why this branch. In many worlds, we're here because this structure allows us to be here. But this raises the meta question, why does mathematics exist? Tegmark would say mathematics doesn't exist in space and time. It's not a thing that needs creating. It's abstract, eternal, necessary. But this feels like kicking the can down the road. We're still left with existence. Instead of a physical universe needing explanation, we have a platonic realm of mathematics needing explanation. And if mathematics is eternal and necessary, why not say the universe is eternal and necessary? We've just swapped one mystery for another. Unless you think mathematics is more fundamental than physics, that mathematical truths are bedrock and physical truths are derived. This is a philosophical position, and it's debated. But it's worth noting how far we've come from the original question. We started asking what came before the Big Bang, and we've arrived at questions about the nature of existence, the role of mathematics, the meaning of causation. This isn't a failure, it's progress. We've traced the question to its roots. We've seen that it branches into multiple questions, each deep and subtle. And we've seen that easy answers don't work. The question resists simple solutions. Let's think about entropy again. The second law of thermodynamics says entropy increases. Disorder grows. Heat flows from hot to cold, not the reverse. This seems obvious now, but it's statistical. It's not a fundamental law like conservation of energy. It's a consequence of probabilities. There are many more disordered states than ordered ones, so systems tend to evolve toward disorder, just by chance. But this means the second law has a direction. It distinguishes past from future. The past is lower entropy. The future is higher entropy. This gives time an arrow, the thermodynamic arrow, and it's the reason we remember the past but not the future. Memories are low entropy structures, formed when entropy was lower in the past. But here's the puzzle. If the universe is currently high entropy and increasing, then it was lower entropy in the past, much lower at the Big Bang. The early universe was incredibly smooth, incredibly uniform. That's low entropy for gravity. High entropy for gravity would be clumpy, with black holes and voids. So the Big Bang was a low entropy state. But why? If the universe started in a random state, it should be high entropy. Low entropy is special, rare, unlikely. This is called the past hypothesis. The assumption that the universe started in a low entropy state. But it's not explained, it's assumed. Some physicists think inflation explains it. Inflation stretches space so smooth that irregularities are erased. The universe becomes uniform, low entropy. But inflation itself requires a low entropy starting state. The inflattened field needs to be in a special configuration. So inflation doesn't solve the problem. It shifts it back one step. Others think the low entropy is a boundary condition, just a fact about the universe, not something that needs explaining. But this feels unsatisfying. We want to know why that boundary condition holds. And here's where things get speculative. Some models suggest time might not have a direction before the Big Bang, or rather, there might be two directions, one forward and one backward from a low entropy center. Imagine the Big Bang as the lowest entropy point. Time extends in both directions from there, both increasing in entropy. There would be another universe on the other side, running backward from our perspective. But to observers there, they're going forward. We're the ones running backward. This is called the two-headed arrow of time, or the Janus point. It's mathematically consistent, but it's weird, and we have no way to test it. The other side is causally disconnected from us. Still, it's a way to explain the low entropy at the Big Bang. It's not special, it's the center. Entropy increases in both directions because that's the only direction from the center. But this assumes a center. And if time has a center, what's at the center? What is the Big Bang in this picture? We're back to the same questions. Let's approach this from yet another direction. Why does the universe have the properties it does? Why 3 dimensions of space and 1 of time? Why these particles? Why these forces? We don't know. These are free parameters in our theories. We measure them, but we don't derive them from deeper principles. Some physicists think a final theory, a theory of everything, would have no free parameters. All properties would be determined by consistency. String theory attempts this. In string theory, particles aren't points. They're tiny loops of string. Different vibration modes of the string correspond to different particles. String theory requires extra dimensions, not just the 3 we see, but 6 or 7 more, curled up so small we don't notice them. The properties of particles depend on how these extra dimensions are curled. Different geometries give different physics, but there are many ways to curl the extra dimensions. Thousands, maybe 10, 500. This is called the string landscape, and it suggests there's no unique solution, no single right answer. Different regions of the landscape correspond to different universes, different laws of physics. If string theory is right, and the landscape is real, then our universe's properties aren't determined by a final theory. They're environmental. We're in one valley of the landscape. Other universes are in other valleys. This is unsatisfying if you wanted a unique answer, but it might be the truth. Nature doesn't owe us uniqueness, but it also means the question, why this universe, becomes anthropic again. We're here because this valley allows life. Other valleys don't. And the deeper question becomes, why does the landscape exist? What determines its structure? String theory doesn't answer that. It's a framework, not a final theory. It assumes certain principles, like supersymmetry and extra dimensions. But why those principles, we don't know. Every theory assumes something. Quantum mechanics assumes Hilbert spaces and operators. General relativity assumes smooth manifolds and the equivalence principle. You can derive a lot from these assumptions, but the assumptions themselves aren't derived. At some point, you hit bedrock. Principles you can't derive from deeper principles, unless there's an infinite regress. Principles all the way down, or unless the principles are necessary. They couldn't be otherwise. But how do you prove necessity? This is where science reaches philosophy, and philosophy, for all its value, doesn't give testable predictions. Let's talk about the observer. In quantum mechanics, observation plays a role. Not observation by a conscious being necessarily, just interaction with a measuring device. When a quantum system interacts with a macroscopic device, the superposition decoheres. The system appears to collapse into a definite state. But what counts as a measuring device? This is the measurement problem, and it's unsolved. Different interpretations of quantum mechanics give different answers. In the Copenhagen interpretation, measurement is fundamental. It's a primitive concept, not reduced to anything more basic. In many worlds, there's no collapse. The system and device enter a superposition. Both outcomes happen in different branches. In de Broglie, Bohm theory, particles have definite positions all along. The wave function guides them, but they're real, not in superposition. These interpretations make the same predictions. They're empirically equivalent, so you can't test which is right, but they have different implications for cosmology. In Copenhagen, you need an observer outside the system to collapse the wave function. But if the system is the universe, there's no outside. So what collapses the universal wave function? This is called the problem of quantum cosmology. In many worlds, there's no problem. The universe doesn't collapse, it branches. Observers are part of the branches. In de Broglie, Bohm, the universe has a definite state all along. No collapse, no branches. So the interpretation you choose affects how you think about the Big Bang. Is the Big Bang a definite event, or a superposition of events, or a branching point? We don't know. And without a resolution to the measurement problem, we can't know. But here's something interesting. Some physicists think consciousness plays a role in collapse. That observation by a conscious being is what collapses the wave function. This is controversial. Most physicists reject it, but a few take it seriously. If consciousness is necessary for collapse, then the universe didn't have definite properties until conscious observers arose. Before that, it was in superposition, a cloud of possibilities. This sounds mystical, but it's a serious interpretation, called the von Neumann-Wigner interpretation. It implies observers aren't separate from reality. They're part of how reality becomes definite. But this raises questions. What counts as conscious? Does a dog count? A bacterium? An AI? And if consciousness is necessary, where did consciousness come from? How did the universe evolve conscious beings if it needed conscious beings to have definite properties? This seems circular, unless consciousness is fundamental, not something that emerges from matter, but something basic, like charge or mass. This is panpsychism, the idea that consciousness, or proto-consciousness, exists everywhere. It's a minority view, but some physicists and philosophers take it seriously. If panpsychism is true, then asking why the universe exists might be the wrong question. Maybe the universe is self-aware in some sense. Maybe existence and awareness are two sides of the same thing. This is highly speculative, and it's not testable, but it's a direction of thought, and it shows how the question, what came before the Big Bang, opens onto other questions. about consciousness, about the nature of reality, about what exists. Let's return to quantum tunneling from nothing. We said the universe might have tunneled from a state of no space-time into a state with space-time. But what does it mean for space-time to not exist? In our experience, everything exists in space and time. Events happen at particular locations at particular times. But in quantum gravity, space-time might be emergent. It might not be fundamental. Some approaches to quantum gravity, like loop quantum gravity, describe space as a network of discrete loops. Space-time is a large-scale approximation, like temperature is a large-scale approximation of molecular motion. At the fundamental level, there's no smooth space-time. There's a quantum network. If that's right, then before the Big Bang, the network was in a different configuration. Maybe a configuration with no large-scale space-time, no dimensions, just a quantum graph. The Big Bang would be the transition from this pre-geometric state to a state with emergent space-time. Before wouldn't mean earlier in time. It would mean a different quantum state, not embedded in time. This is hard to visualize, but mathematically it's coherent, and it changes the question. Instead of asking what came before in time, we ask what quantum state preceded the emergence of time. But preceded still smuggles in temporal language. Maybe we need new language, new concepts. Maybe the question can't be asked in English, only in mathematics. And maybe the answer is an equation, not a narrative. Let's think about nothingness one more time. We've established that physical nothingness, empty space, doesn't exist. The vacuum has energy and structure. But could there be absolute nothingness? No space, no fields, no laws, no mathematics. Some philosophers think absolute nothingness is incoherent, that existence is necessary, that something must exist because nothingness is impossible. One argument: nothingness has no properties, no structure, no constraints. Therefore, anything could arise from it. If anything could arise, something will arise. Therefore, existence is necessary. This is a version of the principle of sufficient reason, the idea that everything has an explanation. But the principle of sufficient reason is debatable. Quantum mechanics suggests some things, like radioactive decay, have no explanation. They just happen. Maybe existence is like that. It doesn't have a reason. It just is. Or maybe the principle of sufficient reason applies only within the universe, not to the universe itself. This is a philosophical move. You're drawing a boundary. Inside the boundary, everything has a cause. Outside, the boundary itself doesn't. But why draw the boundary there? It feels arbitrary. But maybe it's necessary. Maybe explanation has limits. Another argument: absolute nothingness is unstable. We discussed this earlier. If nothingness is symmetric and symmetry can break, then nothingness decays into something. But this assumes quantum mechanics applies to nothingness, which is a big assumption. Still, it's a suggestive idea that existence is more stable than non-existence, that something is easier than nothing. We're used to thinking the opposite, that existence requires effort, maintenance, creation, that nothing is the default. But physics suggests otherwise. Particles pop into existence in the vacuum. Energy fluctuates. The vacuum is active, not passive. Maybe existence is the default and nothingness is the anomaly. This inverts the question. Instead of asking why there's something rather than nothing, we ask why we ever expected nothing. And the answer might be because our intuitions are wrong. Because we evolved in a world where objects are stable and creation seems effortful. But at the quantum level, creation is easy. Existence is common. Nothingness is the hard thing to achieve. Let's consider the role of information again, more carefully. In thermodynamics, entropy measures disorder. In information theory, entropy measures uncertainty. These are connected. Boltzmann showed that thermodynamic entropy is proportional to the logarithm of the number of microstates consistent with a macrostate. So entropy is, in a sense, information. Specifically, it's the information you don't have, the missing information about the microstate. Now, the universe started in a low entropy state, which means it started in a state with low missing information, high information. Where did that information come from? In classical physics, information can be created. You arrange atoms into a pattern, you've created information. But in quantum mechanics, information is conserved. The total information in a closed system doesn't change. So if the universe is a closed system, its information content has been constant since the beginning. The information we observe in galaxies and stars and life was always there. It was just encoded differently. At the Big Bang, the information was in the quantum state, the precise configuration of fields. As the universe evolved, that information manifested macroscopically. But this doesn't explain where the information came from originally, unless the universe isn't closed, unless it's part of a larger system, or unless information isn't fundamental, unless it emerges from something deeper, something that doesn't have information. This is speculative, but it's a direction. Some physicists think space-time itself is emergent from entanglement, that the geometry of space is encoded in quantum entanglement between regions. If that's true, then information is more fundamental than space. Space is a way of organizing information, and the Big Bang would be the emergence of space from a pre-geometric information structure. This is called emergent gravity or entropic gravity. It's not mainstream yet, but it's being explored, and it suggests the ultimate answer to what came before the Big Bang might be information, raw, abstract quantum information, not information about something, just information, structure without substrate. This is almost impossible to visualize, but mathematically you can work with pure information, abstract Hilbert spaces, quantum states, and from those, spacetime might emerge. Let's talk about the role of symmetry one more time, but deeper. In physics, every symmetry corresponds to a conservation law. This is Noether's theorem. Time symmetry gives energy conservation. Space symmetry gives momentum conservation. Rotational symmetry gives angular momentum conservation. These aren't separate facts, they're different aspects of the same thing. Symmetry is fundamental. Now, the laws of physics have symmetries. The electromagnetic field equations are symmetric under rotations. The weak force equations are symmetric under certain transformations. And the most fundamental symmetries are gauge symmetries. These are symmetries where you can change certain quantities at every point in space-time independently, and the physics doesn't change. Gauge symmetries determine the forces. The electromagnetic force comes from Euler-1 gauge symmetry. The weak force comes from SU12. The strong force comes from SU3. So the forces we observe are consequences of symmetries. But why these symmetries? One idea: these are the only consistent symmetries. Any other choice would lead to contradictions. String theory suggests this. In string theory, the gauge symmetries are determined by the geometry of the extra dimensions. Change the geometry, you change the symmetries, you change the forces. But there are many possible geometries, so many possible sets of forces, unless there's a principle that selects one geometry, a principle of maximum symmetry or minimum action or mathematical elegance. This is the dream of a final theory. A theory so constrained by consistency that it's unique, no free parameters, no arbitrary choices. But we're not there yet, and we might never be. It's possible the universe has free parameters, that some things are just facts, not derived from deeper principles. This would be disappointing, but it might be true. Or it might be that the parameters aren't free in a multiverse. They vary across regions, and we observe the values we do for anthropic reasons. Again, this is speculative, but it shows how the question, what came before the Big Bang, connects to the question, why these laws? Both are asking about the origin of structure. Where did the structure of the universe come from? And the answer might be it was always there in some form, or it emerged from symmetry breaking, or it's environmental, varying across a multiverse. We don't know. Let's consider one more idea, the holographic principle. In the 1990s, physicists studying black holes realized something strange. The entropy of a black hole is proportional to its surface area, not its volume. This is weird. Entropy usually scales with volume. More space, more possible microstates, more entropy. But for black holes, it scales with area. This suggests information is stored on the surface, not in the interior. Jacob Bekenstein and Stephen Hawking worked this out, and Leonard Susskind and Gerard Hooft extended it to the holographic principle. The idea: the information in a volume of space is encoded on the boundary of that volume. It's like a hologram, a two-dimensional surface encoding a three-dimensional image. If the holographic principle is right, then our three-dimensional universe might be a projection from a two-dimensional boundary. This sounds absurd, but it's been tested in certain theoretical contexts, like the ADS-CFT correspondence in string theory. In ADS-CFT, a gravitational theory in a higher dimensional space is exactly equivalent to a quantum field theory on the boundary. They're two descriptions of the same thing, so space might be emergent, not fundamental. If space is emergent, then the Big Bang isn't the beginning of space. It's the beginning of the emergent description. At a deeper level, there's a boundary theory, a quantum field theory, evolving according to its own dynamics. The Big Bang is just a feature of how that boundary theory maps to an emergent spacetime. This is highly speculative. ADAS CFT works in a specific context, anti-de Sitter space, which doesn't describe our universe. Our universe is de Sitter with positive cosmological constant, but the idea is suggestive. Maybe spacetime is holographic. Maybe the Big Bang is an emergent phenomenon. And if space and time are emergent, asking what came before the Big Bang is like asking what's underneath the pixels on a screen. The question assumes the screen is fundamental, but it's not. It's a display of underlying data. The underlying data doesn't have a before. It has different states, different configurations, and one configuration corresponds to the Big Bang. This is hard to wrap your mind around, but it's a serious direction in theoretical physics. So where are we? We started with a simple question: what came before the Big Bang? And we've seen that the question is not simple. It assumes time extends before the Big Bang, but time might be part of what the Big Bang created. It assumes there's such a thing as nothing, but physics suggests nothing is unstable, perhaps impossible. It assumes causation applies, but causation might be emergent, not fundamental. It assumes the Big Bang is a beginning, but it might be a transition or a boundary or an emergent feature. Every answer we've considered creates new questions. If the universe tunneled from nothing, what are the laws that govern tunneling? If time began with the Big Bang, what does mean? If spacetime is emergent, what is it emergent from? We haven't answered the question, but we've clarified it. We've seen its depth, its complexity, its connection to the deepest issues in physics and philosophy, and we've seen that physics has made astonishing progress. We understand the universe back to unimaginably early times. We can describe processes that happened when the universe was a fraction of a second old, but the ultimate origin remains beyond our grasp, not because we're not smart enough, but because the origin is tangled with questions about the nature of time, causation, existence itself. We're at the edge of what science can currently say, but the edge is not a wall, it's a frontier, and physicists are pushing against it. New telescopes are being built, new accelerators, new mathematical tools, new ideas. Maybe in our lifetime, we'll resolve the measurement problem, we'll develop quantum gravity, we'll test the multiverse hypothesis, or maybe these questions will remain open for centuries. Either way, the journey is valuable, not because we'll reach a final answer, but because the search deepens our understanding. It reveals the structure of reality. It shows us how the universe works, even if we don't know why. And there's something humbling about this, about standing at the edge of knowledge and seeing how much we don't know. The universe is vast and strange. It doesn't conform to our intuitions. It surprises us. It challenges us. And the biggest surprise might be that the question, what came before the Big Bang, is not the right question. The right question might be something we haven't thought of yet, a question that dissolves the puzzle by showing we were looking at it wrong. This has happened before. People asked what keeps the planets moving. Newton showed the question was wrong. Nothing keeps them moving. They're in free fall. People asked why the universe doesn't collapse under gravity. Einstein showed space itself is dynamic. It can expand. People asked what the ether is that light waves travel through. Special relativity showed there is no ether. The question disappeared. Maybe what came before the Big Bang will disappear too, not because we found the answer, but because we realize the question assumes something false. Maybe time doesn't work the way we think. Maybe causation doesn't work the way we think. Maybe existence doesn't work the way we think. And once we understand that, the question will dissolve. We'll look back and see it was based on a confusion, a misunderstanding of what the universe is. But we're not there yet. We're still asking, still exploring, still building models and testing them. And that's okay. Science is not about having all the answers. It's about asking better questions. And the question, what came before the Big Bang, even if it turns out to be confused, has led us to better questions, deeper questions about the nature of time, about the stability of nothing, about the emergence of space-time, about the role of quantum mechanics in cosmology. These are the questions we're working on now. These are the frontiers, and who knows what we'll discover. Let's think about the fine-tuning problem one more time. The universe has certain constants: the strength of gravity, the mass of the electron, the cosmological constant. These constants seem fine, tuned for life. Change them slightly and stars don't form, or atoms don't form, or the universe expands too fast for galaxies to coalesce. This fine-tuning demands explanation. One explanation: design. Someone or something tuned the constants. But this isn't a scientific explanation. It doesn't make testable predictions. Another explanation: necessity. The constants couldn't be otherwise. They're determined by a deeper theory. But we don't have that theory. Another explanation: the multiverse. The constants vary across regions or universes. We're in a region where they allow life. This is anthropic reasoning. But there's another possibility. Maybe the constants aren't fundamental. Maybe they emerge from the initial conditions of the universe, and the initial conditions were random, but constrained by quantum mechanics. In quantum cosmology, the initial state of the universe is a wave function. This wave function determines the probabilities of different outcomes. If the wave function is peaked around low entropy, high information states, then the universe is likely to start in a state that allows complexity, structure, life. So, the fine-tuning isn't mysterious. It's a consequence of the initial quantum state. But this pushes the question back. Why that wave function? Why is it peaked there? Some proposals, like the Hartle-Hawking no-boundary proposal, derive the wave function from a principle, the principle of no boundary. The universe is finite in the past but has no edge. From this principle, you can calculate the wave function, and it turns out to favor low entropy initial states. So the fine-tuning is explained, not by design, not by multiverse, but by a principle about the geometry of space-time. This is elegant, but it's not confirmed. The Hartle-Hawking proposal makes predictions, but they're vague and hard to test, and it assumes Euclidean quantum gravity, which is not well understood. So we're not sure if this is right, but it's an example of how physics can address seemingly metaphysical questions. Fine, tuning feels like it requires a designer or a multiverse, but maybe it just requires the right initial conditions, determined by a principle. And if that's true, then the universe's properties aren't arbitrary. They're consequences of geometry and quantum mechanics, which means the question, why this universe, has an answer, a physical answer, not a metaphysical one. But we're not there yet. Let's return to the idea of time as emergent. In general relativity, time is part of the geometry. It's a dimension. It curves and stretches. But in quantum mechanics, time is a parameter. It's not an observable. You can't measure it the way you measure position or momentum. This creates a tension. In quantum gravity, is time a dimension or a parameter? Some approaches treat time as fundamental. Others treat it as emergent. In the Wheeler-DeWitt equation, which is an attempt at quantum cosmology, time disappears. The equation describes a static wave function. No time evolution. This is called the problem of time. If the wave function is static, how do we observe change? One answer: time is emergent. It arises from correlations within the wave function. What we perceive as time is actually the unfolding of these correlations. This is deeply weird. It means time isn't fundamental. It's a macroscopic approximation. At the fundamental level, the universe is timeless, a static mathematical object, but we, embedded within it, perceive time. Because our memories and perceptions are correlated with the rest of the universe in a particular way. If this is right, then the Big Bang isn't an event in time. It's a boundary in the timeless wave function, a region where correlations are minimal. And asking what came before the Big Bang is like asking what's outside the wave function. The question doesn't make sense. The wave function is all there is. This is the block universe taken to an extreme. Not just that past and future are equally real, but that time itself is an illusion, a useful fiction our minds construct. This is hard to accept. Time feels real. It feels like the most fundamental aspect of experience. But physics has overturned intuition before. We used to think the Earth was stationary. It feels stationary, but it's not. We used to think time was absolute. It feels absolute, but it's not. Maybe we'll come to think time is emergent. It feels fundamental, but it's not. This would be a profound shift. But science is full of profound shifts. And if time is emergent, then the question, what came before the Big Bang, dissolves. There is no before. There's only the timeless structure of the wave function. But this is speculative. The problem of time is unsolved. Different approaches to quantum gravity give different answers. In loop quantum gravity, time is semi-classical. In string theory, time is often treated as fundamental. We don't know which is right. Let's think about consciousness one more time. We mentioned the von Neumann-Wigner interpretation, where consciousness collapses the wave function. This seems to give consciousness a fundamental role. Observers aren't passive, they shape reality. But most physicists reject this. Consciousness is a product of the brain. The brain is a physical system. Physical systems don't have special quantum properties. Decoherence explains why macroscopic objects appear classical. Their quantum superpositions become entangled with the environment, and the phases wash out. What's left looks like a classical probability distribution. No consciousness needed. But some argue decoherence doesn't solve the measurement problem. It explains why we observe definite outcomes, but it doesn't explain why a particular outcome occurs. Why this branch of the wave function rather than that one? In many worlds, all branches occur. No problem. In Copenhagen, measurement is primitive. No explanation. In von Neumann, Wigner, consciousness selects a branch. Each interpretation has problems. None is fully satisfying. But for our question, the measurement problem is relevant. Because if consciousness plays a role, then the universe before conscious observers is different from the universe after. Before observers, the universe is in superposition, a cloud of possibilities. After observers, it has definite properties. The Big Bang, in this view, isn't fully real until observed. It's a retrocausal process. Observers now determine what happened then. This sounds crazy, but quantum mechanics has retrocausal elements. The delayed choice experiment shows that decisions made now affect how we interpret the past. It's not time travel. It's not changing the past. It's that the past wasn't definite until observed. If this is right, then the Big Bang is entangled with us. We're part of making it real. This is a radical idea, and most physicists don't accept it. But it's worth considering, because if it's right, then the question, what came before the Big Bang, is incoherent in a new way. The Big Bang isn't independent of us. It's part of the same quantum system we are. Asking about it in isolation is like asking about one half of an entangled pair without reference to the other. The question is incomplete. But again, this is speculative. The measurement problem is unsolved, and until it's solved, we can't say for sure what role, if any, consciousness plays. Let's consider emergence one more time, more broadly. Emergence is when complex properties arise from simple rules. A flock of birds moving in unison. No bird knows the overall pattern. They just follow local rules. But the flock has structure. In physics, temperature is emergent. It doesn't make sense for a single molecule. It's a property of large collections. Pressure is emergent. Sound waves are emergent. Even solid matter, the sensation of a table being hard, is emergent. It's an electromagnetic repulsion between electron clouds, but it feels like solidity. So emergence is everywhere. And some physicists think space-time itself is emergent, that at the fundamental level there's no space or time, just quantum information or spin networks or strings. Space-time is a large-scale approximation, like how a fluid is an approximation of discrete molecules. If space-time is emergent, then the Big Bang is emergent. It's a feature of the emergent description, not the fundamental level. At the fundamental level, there's no beginning. There's a quantum state evolving according to timeless equations. Or not evolving, if time itself is emergent. The Big Bang is what that state looks like when you grain it. When you zoom out and describe it in terms of space-time, this is a profound shift in perspective. The Big Bang isn't the origin of reality. It's a useful fiction, a way of organizing the data. The origin, if there is one, is at the fundamental level, and at that level, there might be no origin. Just existence, timeless and necessary. But we don't have a theory of the fundamental level yet. We have candidates. String theory, loop quantum gravity, causal set theory, others. Each makes different assumptions. Each has different implications, and none is confirmed. So we're speculating, but it's informed speculation, based on principles, mathematics, consistency. And speculation is how science advances. You propose an idea, you derive predictions, you test them. If it works, you refine it. If it doesn't, you discard it. This is the process. It's slow, it's uncertain, but it's how we learn. Let's think about the anthropic principle more carefully. The weak anthropic principle says we observe a universe compatible with our existence because we couldn't exist in an incompatible one. This is trivial, but it has consequences. If there are many universes, or many regions with different properties, we're necessarily in one that allows life. So the properties we observe might not be typical, they might be rare. This is selection bias. Like how lottery winners think winning is common. They're biased because they won. The strong anthropic principle says the universe must have properties compatible with the emergence of observers at some point. This is more controversial. It sounds like teleology, like the universe is designed for observers, but it's not necessarily teleological. In a multiverse, the strong anthropic principle is just a prediction. Most regions don't have observers. We're in one that does. No design needed. But the anthropic principle is frustrating. It doesn't explain why the constants have the values they do. It just says we couldn't observe different values. This feels like giving up, like saying, is what it is. But it might be the truth. If the multiverse is real, and the constants vary, then anthropic reasoning might be the only explanation available. We won't derive the electron mass from a deeper theory. We'll just observe it's the right value for life, and that makes sense given selection bias. This would be disappointing, but disappointment isn't an argument. Nature doesn't care about our preferences. Still, some physicists hope the constants are determined by a final theory, that there's no multiverse, just one universe with unique properties. This is a more satisfying answer, but we don't know if it's right, and the fine-tuning problem is so severe that many physicists lean toward the multiverse. The cosmological constant, for instance, is so absurdly small that it's hard to imagine it's a coincidence. If it varies across a multiverse, and most regions have a large value, then we're in a rare region with a small value, because large values don't allow galaxies. This makes sense, but it's not testable. We can't observe other universes, so the anthropic principle is both powerful and frustrating. It answers some questions, but it closes off others. And for our question, what came before the Big Bang? The anthropic principle doesn't help. It tells us we observe a universe that began, but it doesn't tell us why it began or what came before. Unless you think the multiverse is eternal, and our universe is a fluctuation within it, then there's no ultimate beginning, just local beginnings in different regions. This is possible, but again, speculative. 2. Let's consider the role of nothing one last time from a different angle. We've said nothingness might be unstable. It might decay into something. But there's another possibility. Maybe nothingness is impossible. In quantum field theory, the vacuum is the lowest energy state, but even the vacuum has energy, 0-point energy. This suggests energy can't be zero. There's always something. And if energy can't be zero, then nothing can't exist, because nothing would have zero energy. So existence is mandatory, not because something caused it, but because the alternative is impossible. This is a strange idea, but it fits with quantum mechanics. In quantum mechanics, you can't have zero uncertainty. Position and momentum can't both be known exactly. Energy and time can't both be zero. There's always fluctuation, always activity. The universe can't settle into perfect stillness. It's prohibited by the uncertainty principle. So nothing, in the sense of perfect stillness, perfect absence, is forbidden. Existence is the only option. This inverts the usual question. Instead of asking why there's something rather than nothing, we ask why nothing was ever considered possible. And the answer is because our classical intuitions mislead us. We think objects can be at rest, can have zero energy. But quantum mechanics says no. There's always motion, always energy, always something. This doesn't explain why quantum mechanics is true, but it suggests that given quantum mechanics, existence is necessary. And if quantum mechanics is a consequence of deeper principles like consistency or symmetry, then existence might be logically necessary, not caused, not created, just necessary. This is a form of answer, not a satisfying one perhaps, but an answer. The universe exists because non-existence is incoherent. So let's step back and take stock. We've explored many ideas. Quantum tunneling from nothing, time as emergent, space-time as holographic, the multiverse, the anthropic principle, the instability of symmetry, the role of consciousness, the problem of time. Each offers a perspective on the question, what came before the Big Bang? And each dissolves the question in a different way. If time began with the Big Bang, there's no before. If nothing is unstable, existence is necessary. If space-time is emergent, the Big Bang is a feature of the emergent description. If the multiverse is eternal, our Big Bang is a local fluctuation. If consciousness selects reality, the Big Bang is entangled with observation. These aren't contradictory, they're complementary, different facets of the same mystery. And the mystery is this: why is there something rather than nothing? Physics has made progress on this question. It's shown that nothing is harder to achieve than something. That existence might be more natural than non-existence, but it hasn't answered the question, not definitively. Maybe it never will. Maybe the question is beyond the scope of science. Maybe it's metaphysical, not physical. Or maybe we just need more time, more data, more theoretical breakthroughs. Quantum gravity, when we have it, might change everything. It might show that time and space are illusions, that the universe is a timeless mathematical structure. Or it might show something else entirely, something we haven't imagined. That's the nature of exploration. You don't know what you'll find, but you keep looking, because the search itself is valuable. It deepens understanding. It reveals the structure of reality. And even if we never answer what came before the Big Bang, we'll have learned astonishing things along the way. We'll have seen how time and space are woven together, how quantum mechanics challenges our intuitions, how the universe is stranger and more beautiful than we imagined. And that's worth it. Let's end with a quiet thought. The universe exists, that's a fact. Whether it began or has always been, whether it's one of many or unique, it exists, and we exist within it. Conscious beings asking questions. The fact that we can ask, what came before the Big Bang, is remarkable. It requires a universe old enough for stars to form, for planets to cool, for life to evolve, for brains to develop. It requires 13.8 billion years of cosmic evolution. So the question carries its own answer, in a sense. The universe must be old. It must have started in a low entropy state. It must have laws that allow complexity. Otherwise, we wouldn't be here to ask. This is the anthropic principle again, but it's also a kind of gratitude. We're part of something vast, a universe that began in a hot, dense state and expanded into the cold, sparse expanse we observe. A universe that evolved structure, galaxies, stars, planets, life. We're made of atoms forged in stars. We're the universe reflecting on itself. And the question, what came before the Big Bang, is the universe asking about its own origin. There's something poetic about that. We might never know the answer, but the question connects us to the deepest mysteries, to the nature of time, existence, causation. It reminds us how much we don't know, how much remains to explore, and maybe that's the point, not to arrive at a final answer, but to keep asking, keep wondering, keep pushing the boundaries of knowledge, because the universe is not a puzzle to be solved and set aside. It's an ongoing mystery, and we're part of it. The Big Bang isn't just an event in the past. It's the origin of everything we are, every atom in our bodies, every thought in our minds. We're living inside the question, and perhaps the answer isn't something we find out there in the cosmos. Perhaps it's something we discover in here, in the very act of asking. Not because the answer is subjective, but because asking the question changes us. It expands our minds. It makes us see the universe differently. And in that seeing, in that shift of perspective, we touch something true. Not a final truth, not an answer that closes all questions, but a truth nonetheless. The truth that existence is strange, that reality is deeper than it appears, that the universe rewards curiosity. And maybe that's enough. Maybe the question, what came before the Big Bang, isn't meant to be answered. It's meant to be lived with, to be carried as a reminder that we're part of something larger, something that began or didn't, in a way we can barely comprehend. And that's okay. We don't need to understand everything. We just need to keep asking, keep exploring, keep marveling at the fact that we're here at all. Because existence, however it came to be, is astonishing. And the Big Bang, whether it's a beginning or a boundary or an emergence, is part of that astonishment. So we don't conclude. We don't wrap it up neatly. We let the question linger. What came before the Big Bang? Maybe nothing. Maybe something. Maybe the question is wrong. But the wondering, the deep, quiet wondering, that's real. And it will continue long after this script ends. Long after we stop speaking, the question will remain. And somewhere someone will ask it again. And the universe, silent and vast, will offer no answer. Only the invitation to look deeper,